unnecessary or impossible to determine the size of particle, or the size of certain particle. Okay, but it's important to determine the particle size distribution. Here we classify size particles to the green group. What green group? Particle grouped by its size. But this green group relate to the properties of the source. Here we classify the particle which have the similar shape or similar size and properties. So the green group like this, the fine grain soil or coarse grain soil or high grain soil. Okay. Here 0.075. Definitely the fine grain soil, maybe the diameters less than 0.075 millimeters. We call fine grain soil. Okay. When diameters in the between the 0.075 millimeters and the 16 millimeters, we call coarse grain soil. Okay. Diameters more than 16 millimeters, we call high grain soil. But the soil particle or the natural soil is a assemblage of various kind of size. So we should separate the type of the green group. How to determine the green group to separate various kind of grain or particle grain? Here we use the particle size distribution curve. This particle size distribution is expressed by a plot of person divided by width with diameters in millimeters, like this. Maybe the parental coordinate with represent the particle size. We use diameters, but so particles not a spatial or a circular, but we assume it's a circular shape. Okay, so we use the diameters. But here the coordinate in logarithmic, okay, and the y-axis represents percent divided by week. This represent percentage week, no more than a certain diameters, no more than yes, maybe the mass percentage, no more than a certain diameter. Okay, here the diameter and this mass percentage. For example, we use a case to explain the curve, how to draw the curve. Okay. For example, here we have a soil sample, maybe 1,000 gram. Okay, and we use the sieve method or the segmental or sinking method and determine the particle size like this, maybe this diameters, okay, so particle size here 2 millimeters, and here 1 millimeters or 0.5 or 0.25, 0.15, and 0.075 millimeters. Okay, maybe here we have a series of seed net like this, and we obtain the mass of soil retained on each seed.
Which page?
In our
Page
8, okay? Yes. Here the text, the result of text. From this result, the mass of depend on each thing. Maybe here the mass more than 2 millimeters. And the next between the 2 millimeters and 1 millimeter, okay? And 25 gram between 0.5 millimeters and 1 millimeters, like this, okay? So we can determine no more than a certain diameters. For example, less than 2 millimeters, maybe the mass use 1,000 minus 100. That's right? Yeah, maybe this more than 2 millimeters. Okay, so here we use 9 gram. And this less than 1 millimeter mass, maybe 80 gram. Okay, and this
70.
maybe okay. Maybe 900, 800, and 550, 100, and this. And here. Maybe next day, the answer next day 0.75 millimeters, the mass 100 gram, okay? And the diameter last day 0.15 millimeters,
150 gram.
maybe 115 gram. Okay. Next, we use the mass divided by the total mass. Okay. Here, maybe 19%. Here, 18%. Here, 55%. Yes, 25%. Yes,
50%.
55,
This is 10%.
and 10%. Okay. We obtain the result
This
as
is
you choose.
all will be plus, right? That will be
Maybe this, no, next than 2 millimeters, wait, the
90%.
percentage, mass percentage, no more than or less than 2 millimeters, the soil particle mass. Okay, we use percentage, mass percentage. Maybe there's 19%. So we can choose figures like this. here we use the percentage, maybe 90%, and corresponding the diameters, maybe 2 millimeters. Okay. Or 90% corresponding the 1 millimeter. Okay. So we can do
Now she,
rod. Okay.
now she, is there any formula? Is there any formula? Yes, how to calculate?
This maybe it's a cell width of the sieve net, the size of cell width sieve net we use
This one.
This is spiral.
like this. Sieve method. Here, set of sieve net of sieve. Maybe this 2 millimeters or 1 millimeters or 0.5 millimeters or 0.25 millimeters. And use the sieve method to determine the mass. Okay. Maybe we use a soil sample in the sieve, and we check the sieve and some small particle size well due to the nest sieve nest. Okay, and we check the sieve with the soil particle due to the nest or to the nest. Okay, so we can use the sieve method to determine the mass. Next, a certain diameter
Less than 2 millimeters.
of problem.
Less than 2 millimeters actually. This is less than 2 millimeters.
Oh, 2 millimeter. The diameters maybe size of the sieve net. Maybe the sieve net like this. Right? A series of the sieve net, and we check the soil sample, and the small size particles will due to nest. Okay, so we can separate a various kind of particle. Okay. Here, the diameter, not the soil diameter, but the sieve diameter. Okay.
Yeah.
So, use this method, we can obtain the figures. we use the figures, the particle size distribution curve. We use this curve to assign the source gradient. Size source gradient, okay, or source gradation. Here we have some characteristic particle size. D50 mean diameter. It represent maybe at diameter 50. The percentage is 15%. Maybe less than diameter 50. The mass percentage is 50. Okay, so we call mean diameters. Maybe the mass percentage is 50. Okay, and then we use D60. D60 means source diameter at which 16% of the source weight is fatter. Or we can say less than D60, the source mass percentage is 16%. Okay, and D10 or D30 or D30. Maybe here 10%. So diameters at which 10% of the source weight fatter. Okay. So what D30 from above we can determine maybe D30 so diameters at which 13% of the source weight is fatter. Okay, so from the figures we can determine the characteristic particle size like this. And next we use the characteristic particle size to calculate uniformity. CU coefficient, uniformity coefficient or coefficient of uniformity mean D16 divided by D10. We use two diameters of the source particle. D16 is source diameter at which 16% of the source weight is fatter. And D10 also source diameter, but at which 10% 10% of the soil weight is valid. Okay? So from the figure, we can obtain the CUs in the 10% and the 16%, maybe in y-axis. And the parental coordinate is D16 and D10. Use this distance or the ratio of the two diameters. Maybe it represents the snow of the curve. Is that right? Maybe the snow. Here, the vertical coordinate keep constant with the 10% or 16%. Okay, it have the same height. Here's 16%. Here's 10%. Maybe height is constant. Okay, and here's the parental coordinate. And this D16 and this D10 and the coefficient of activity represent the snow. Is that right? Okay, with the snow. So when the unformatted coefficient is larger, maybe this in parental coordinate, the distance between D16 and D10 is larger. Maybe it presents the curved snow. Curved snow is smooth. But if the value is small, represent the distance. The parental coordinate, the distance is small. Maybe the snow is dead. Okay? So we can use the shape of the curve or the snow of the curve to assess the soil grading. Okay? Here we have snow means percent is certain area of particle size. If the snow is dead, means more particles of this size. but it's smooth means less particle of this size. It stays maybe the Cu, the value of Cu is small.
More than five.
If the curve is smooth, the slope is smooth, maybe the value
Yes.
of is bigger. Okay,
Actually,
Actually, said it's smooth. If it's smooth, then less.
as that smooth, maybe the slope,
if it's the Cu is bigger than 5,
okay. Here we have two figures. Okay, one like this, or one like what A source sample, maybe B source sample. Here, which slope is that? Maybe A. Okay, so we call A steep snow and the B smooth snow. Okay, so which soil sample have a well graded? Wells or good gradation, which
which one?
This
soil sample?
A.
B.
Maybe B. Yes. Why? Why B have a good
Or because the Cu is less. the
yes? Maybe the
Cu
value of Cu is bigger.
bigger.
Okay, represent in a certain certain percentage, maybe the particle size have a big range. Okay, so because it have a good gradation. So we use the values of Cu to assess the soil gradation. Or we can use the figure or the curve to assess the soil gradation. Okay?
Actually, what is the standard of Cu? The standard of the coefficient
What
is Cu. Must be
Cu?
more than which value?
Oh, yes, that well, how you the Cu's more than 5.
5%.
Yes, more than 5, maybe good gradation. Okay, maybe the soil have good gradation. But here have a complicated condition or a specific condition. And if the soil sample C have a step, okay, here maybe a horizontal step. What this means?
There is
If have a good condition,
Not good.
not good condition. Why? What the traders?
Because
Maybe in this,
the particular
between this particle size, okay? At this range of particle size, maybe the percentage, the mass percentage is same, means maybe this range of particle size is not. Is that right? Maybe the particle size is not at in this range.
yeah,
Not some range of the soul particle. So the percentage of mass is same, maybe less than diameter 1 and less than diameter 2. Maybe the mass percentage have the same values. So the particle size between diameter 1 and diameter 2
It's not same.
is nothing. Okay? So this soil sample bad gradation, not good gradation. Okay? So here we have a computed value, computed coefficient. And vertical component represent percentage factor by weight, maybe less than a certain particle size. The mass percentage, okay? From this curve, we can give some characteristic particle size, like D15, D16, D10, or D30. It means soil diameters at which 50% or 16% or 10% or 30% of the soil weight is 5. And we can calculate two coefficients. Uniformity and uniformity CU equals D60 divided by D10. Okay. And if the values less than 5, maybe the soil is uniform. Okay. And another coefficient to describe quantities, we use CC. Equal the square D30 divided by D60 and D10. Okay. We call it convergence coefficient. It describes the shape of the curve, and these values describe the slope of the curve. Okay, maybe A have a steep node, B have a smooth node, but C have a step. If the feature or the curve have a step, maybe the CC more than 3 or less than 1. So usually for a good gradation, maybe CC between 1 and 3. Okay. From this result, like this, I have a question. Could you tell me what the value of uniformity coefficient or the conversion coefficient? Use this result, the particle size in this table. What the CU, we use D16, this 0.33, okay, and D10, 0.005. So we use the ratio of the two diameter. Okay, maybe it's more than 5. So the soil sample have good gradation, but we also calculate the CC, the conversion coefficient. Here, D13, here D13, 0.003, here grams, and D16, 0.33, and D10, 0.005. Okay. You can calculate this
Yes.
to that it matter is in the range of 1 and 10, or 1 and 3. Okay. If the value in the range, maybe good gradation. This the result like this. CU equal 16.6, more than 5. Okay, and CC equal 2.41, maybe in the range of 1 and 3. So
2.4.
yes, 2.41. Here maybe 66.
66, yeah.
Okay. So we can draw a conclusion. The soil have a good gradation. Okay. Okay. There's two value, two coefficients to assess the soil particle distribution quantitatively. But another way we use the figures to assess the soil gradation. If the snow is dead, maybe the soil have a uniform particle size. If the snow is smooth, maybe soil have a good gradation. Okay. If a step exists, it represents some range of particle size is nothing, or in lack of particle size, lack of particle size. From the value of Cc, when the Cc is smaller than 1, maybe lack of larger particles. Cc larger than 3, maybe lack of smaller particles. Okay. For good gradation, the Cc equals 1 and 3, between 1 and 3. Okay.
Laoshi, when the Cc curvature is larger than 1, is mean that we don't have we don't have it's smaller when it's smaller than 1, lack of larger particle.
Yes, lack of large particle.
And when is
small lack
more than
of
3.
smaller particle.
Okay.
Yes.
That means it's not good. If it's more
Reason,
yeah.
you want to know the reason or why?
I said if we find that the Cc is more than 2, it's not good.
More than
If it's
1, more than 3 or less than 1,
it's not good.
not good.
Oh.
Not good.
Okay.
So, from the particle size distribution curve, we can know the curve can classify soil. Use the curve, we can classify soil. Cu is used to judge whether soil is uniform or not. Cu more than 5, not uniform. Cu less